Thank you, Leah, for the kind introduction, and welcome everybody also from my side. I hope you enjoy your lunch. I try to put together slides also while eating lunch to ensure that it is a more lightweight presentation. But I hope that I can bring you closer a bit the Energy Hub Demonstrator, which is our demonstrator for district-sized energy systems, buildings, and mobility at ENPA. It is an interesting field from my perspective because we see a lot of changes exactly at this bottom-up level when it comes to what has been triggered by the energy strategy, by the more commonly pull and or push to more sustainability. And from there, that a lot of new technologies are installed, not centrally large power plants or storages, but a lot is happening at the building level, in every building with new technologies like heat pumps or PVs on the roof, electric mobility. And so everything that's going on in the district, there is quite some movement at the moment. And this movement also brings potential for energetic flexibility, i.e. to utilize these technologies not just for the local purpose, but also for other stakeholders along the energy sector value chain. And this is possible because all these new technologies are potentially, or probably all of them, are digitalized in a sense that they have microcontrollers, they have an IP interface, they speak internet protocol. So technically we can communicate with them, read out data, or ideally then also operate them in such a way that it is beneficial. When we look at the digital readiness level of different sectors, however, we see that there are quite some benchmarks around, like consumable electronics, supply chain management, mobility is quite developed as well, logistics. And then more on the follower end of the spectrum is buildings, construction area, and the energy system as a whole. And the idea or the main aim of Energy Hub Demonstrator is to provide a platform where these ideas from the benchmarks can be analyzed, further developed or adapted such that they can have a beneficial impact on the energy sector. Or the other perspective, of course, from the energy sector, see which ideas are beneficial and then try to bring the stakeholders actually to using them by means of having a platform where we can develop them with real-time data or a real-time playground, and having them actually implemented such that people can come and we show them how an approach works, what is necessary for an approach, or how people need to work together such that this approach benefits all of them. It's not just that this should be an ENPA only tool, should be an open platform. So also for other research institutes, or generally also for companies to utilize what we have built up for their developments and to sanity check them, to have a prototype implementation of that, and of course also to showcase that. From my personal research perspective, we use the Energy Hub Demonstrator for learning-based control methods, as you see in the bottom. So also the case studies that I'm going to show you later on are more from that perspective. Now, what does Energy Hub consist of? Let's start with the physical setup. We have two large infrastructures there. One is Nest, that's ENPA's building and building technology demonstrator, where we have different units. We call them units, but it's basically office spaces or residential areas built. And these are added one per year. That I'm not lying, to make sure that I'm not lying to you, we see here a short sketch. In the beginning was nothing, that was 2015. First, of course, we had to build the central infrastructure hosting the units where the district energy system is also installed, our so-called backbone. With the opening, we have the first two units, Vision Wood and Meet to Create, a residential unit for 2 students and an office space. And then over time, we see the solar fitness and wellness, the DFAB house implemented. Here, Solace together with EPFL is implemented. And then more to recent times, we see here the building site of Hilo. And here in the back, we have the Sprint unit, our latest addition. And this is how Nest currently looks like. Next year, this platform on the back will be filled. So this is a living platform in a sense, but from the energy perspective, I mean, we have new technologies, we have new energy demands, energy profiles that we have to take care of all the time, or over the years at least. Currently, there are a couple of thermal technologies, electrical technologies, also interlinking technologies in there, also networks, and the latest addition from the district energy components is an edge data center that we integrated thermally and electrically to see what role plays the increased role of edge computing potentially in a district by showcasing this in Nest. At the moment, we have around these 10,000 data points that we store, and all of that results in a 24/7 multi-energy system. I labeled it 24/7 because it's not just in operation when we have a research project going on, but rather people live and work there, right? So we have to heat regardless if there's a project going on, which also means that we have a state of industry level control setup as a benchmark, which most time is the source of our data collection. And for dedicated research projects, we can oversteer this state of industry control level by whatever the researcher has developed to see, does the approach bring any benefits compared to measured KPIs. Measurements are typically in the thermal world on a 20-second interval level. Electricals are a bit faster, but as we have different units also installed by different companies and planned by different companies, we don't have one type of thermal sensors, for example, but rather a heterogeneous set, which are then all collected into the database. And yes, as we already mentioned, we started in 2017 with the logging of the data in this 1-minute resolution. If we overlay a little bit more technical scheme, we see, okay, these technologies, these are actually located in the units, right? So they have buffer tanks there. The fitness and wellness has an own heat pump, PV system, storage, because this is how you would build a fitness center, a gym with a spa area, local technologies. They don't draw all what they need from the district. And also for the residential and office areas, likewise. However, in the basement, so underground, we also have district size energy systems, 100 kilowatt hour battery storage, thermal storages, ground heat exchangers, and so forth. Just to give you an idea about these district size setup, because with these units as buildings, we can say that we have a district with up to 15 buildings, which can be compared to a real sized or small sized district. In the back, we have moved mobility demonstrator. Everything that Nest is for building technologies. Move represents the mobility aspect. So charging station, hydrogen production for fueling stations, methanation plant, and so forth. Okay, more on the virtual side, how we integrated this is we don't have to go there to actually do control experiments or energy management experiments. Every data point is collected on a virtual environment currently hosted by Swisscom, so remotely. And we give researchers access to this platform that they have access to all the data, all the schematics, all the descriptions, and also the possibility to then feedback control signals to the actual hardware. This is also how my group uses the setup. 2 examples, one more on within a room or within a building, and the second one then a bit more on a systemic level. So out of these 10,000 data points, here we have 5 of them for in the example of the Meet to Create unit, which is an office space. We took ventilation flow rates of inflow rate and outflow air, indoor temperature, and CO2 concentration of the air. And the question was, can we use that data to train networks which indicate presence? So if someone is in the room or not. And of course, having the presence sensor, we have one there to serve as ground truth to train the sensor to. And then in the second step, if we can show that this works, can we also use a developed version of this algorithm to be able to predict presence? So will someone be there in 2 hours, in 4 hours, in 6 hours time, based on the collected data that we have in the database? What for? Good question. There is a nice study, not from us, but I gave you the pointer here, to a study that identified 49 use cases for smart office applications, or for use cases in smart buildings, with office as the main focus. And knowing if someone is there enables a lot of these use cases. For example, if nobody is there and I know that nobody will be coming, I don't have to heat the room. Or if nobody is there and nobody was there, I don't have to clean the room. So staffing can be allocated more efficiently. I can conserve power and so forth. There are 49 of these. Quite interesting. And first of all, did it work? Yes, it did. We looked at different network configurations. And here I'm just showing you the results of the best one, showing that for the prediction, we have around 88 or 86% accuracy in looking at other measurements to indicate is someone there, to indicate presence learned by the network, and then 1 hour in advance, up to 2 hours in advance, and so forth, up to 6 hours in advance, estimating will someone come to the room or not, which is significantly better compared to a naive reference model. So can such a network be trained? Yes. Can it predict? Also, arguably, yes. And what we then did is took one of these use cases, which is room temperature control, and used this algorithm to give the prediction model an indication if it needs to heat the room certain hours in the future or not, or does the room need to be warm in the future or not. I'm a control engineer. I like to close loop. So we fed this back to the room and compared it to different controller setups. On the top, we see the baseline, the state of industry control that just tries to keep 24 degrees. We see in blue, roughly enables that. This is in summer, so we try to cool the room here and not to heat. So whenever the valve is open, indicated in green, cooling energy goes into the room and the temperature should decrease. And it was quite hot. We see in yellow the ambient temperature, so there was actually need to control. Then this is state of industry, then more state of the art, vanilla model predictive control that tries to be more to the comfort bound and save energy at the same time, performs a bit better a subsequent week. And then the one with added occupancy forecast, we see the valve needs to be opened for less. However, this would be compared apples with pears, because in this week and also in this one, it was significantly warmer than in the one where we applied the new controller, meaning we need to have a fair comparison scheme. And one way to do this is with cooling degree days. For heating case, the same thing exists for heating degree days, basically meaning if we have an average ambient temperature of 16 degrees, what was the accumulated energy during that day? Or if we have an ambient temperature of 2 degrees above 16 degrees, so 18 degrees, what was the accumulated energy then? And we should see an increase of needed cooling energy the warmer it gets away from this benchmark, which is actually what we see in blue, the benchmark controller, state of industry, which is always running if no research is going on. Thus, we have a lot of data that we can aggregate to points. Showing the steepest curve, so the highest energy consumption, the predictive controller, vanilla MPC, already is able to reduce by trend the energy consumption, and then with the occupancy forecast, even more so, thus getting away circumventing different ambient temperatures and finding a way to compare different days on the actual system. And the nice benefit is this cooling degree days and heating degree days is a metric known in industry. So when I tell cooling degree days to an HVAC planner or installer, they know what I'm talking about. They can relate to the energy savings there and what this supplies, which is quite nice. Okay, taking one step back, more on systemic level, in one building, we now saw that we can adapt energy intake such that it satisfies minimal energy consumption or more comfort, but we can couple this also to a more district size problem like providing electric energy reserves, secondary frequency reserves in this case, with the district size heat pump. And in this setup, we looked at, okay, we have a heat pump, we have a storage, the heat pump fills the storage, and then the buildings, the units, the rooms deplete the storage because they need the heat in winter or they need the cooling energy in summer. How much reserves can we already provide only with this very small storage? And then how does this increase if we add the controllability or the knowledge of the rooms in the same control regime? So real representation again, that's the heat pump in the basement that you used. The storages for thermal heating energy and cooling energy, they look the same, one picture. And then 2 units were controlled, so were included in this control scheme, and the rest not, just to see what's the marginal effect of that. A little bit more abstract, here are the control loops. We see again the heat pump that impacts the storage, the buildings that we can control, the other knowledge of them, which is fed back into the controller to control the heat pump and the energy intake into the room optimally, such that we can satisfy a frequency, a flexibility window, which was announced the day prior. And the scheme goes as follows. We announced for the next day what flexibility windows we can provide to the transmission system operator. And then the subsequent day, we try to follow the advertised path. And if during a flexibility window, flexibility is needed, the TSO gives us directly the signal, and we have to adjust the operation of the heat pump accordingly. In time series, this looks like this. Announced windows are 15 minutes. And here we provide no flexibility because we estimated that storage too small or demand too high, whatever. And here we see in red an area of flexibility that we announced to the TSO, the transmission system operator. And during these windows, we have to follow the signal that the TSO provides us every 2 seconds. And being able to provide this flexibility gives added value to the transmission system operator. And if the local controller works ideally or well enough, then local energy consumption should not increase and comfort can be satisfied. We applied this to the actual setup for a couple of days to benchmark if everything works in real life. And from the collected data, we crafted a simulation model to be able to have indications of what happens if this would run the whole year for heating and cooling, which is a bit more intuitive than just a couple of days of experiments. And here we see over the period of 1 year that the heating demand, of course, in winter, the cooling demand more in summer. And then in black, the reserves that we can provide only with the small storage. And then the second case in green, if we add the controllability of the 2 units on top of that or include that. And interesting enough, the provided reserves are more during peak times and not during spring and autumn, which also would have been a hypothesis that flexibility would be then. No, we see that when we have peak cooling and peak heating demand. And only with this small storage already, we can provide 3% of the needed energy demand as flexible. We can sell it as flexible energy if we wanted to, which doesn't look like a lot, but the storage isn't really a storage, it's more of a buffer tank. So this is already astonishing that we have 3% of the energy demand covered by that. And now the really surprising part, if we add these 2 units in the control scheme, which represents 7%, only 7% of the heating demand, the offered reserves almost triple, 2.7 times higher than if we would only have the local storage, which is quite interesting. And we wouldn't have been able to figure out these physical boundary conditions or specialities of the local setup if we would just have simulation models, which would be arbitrary. So this has been validated on the real system that we can track this 2-second signal and the results after that. How does one use Energy Hub? taking a step back from the examples, a researcher has to fill out a form that you can find here, just that we know that you exist and that you get your credentials and password, and that we more or less know what you're trying to do. And from there, you can access clients. These are even on the public Wikipedia, so you can access the clients now if you would want to. These are typically the Python client, a MATLAB client, and an R client, depending on the preference of the researcher, or the interfaces of a REST API, a Grafana visualization tool, or the access to the actual SQL database where you really can kneel into historical data. On the wiki page, stuff should be self-explanatory because we intend the open platform to be used by as many people as possible, such that we, as providing the service, don't have to hold everybody by the hand, but that they can query all information that they need from the wiki. For some visualization tools, we also have tutorial videos where you see how to click through how the process goes until you get your time series. For the example of the Python client, how does this look like if you want to do an experiment? First of all, schedule or having access, sure. Then schedule the experiment, again, for the example of the heat pump. Typically, the system is in operation or operated by a local controller, a PLC. There, the state of industry controller is implemented, right? That just switches on the heat pump if heat is needed. Nothing predictive, nothing fancy, state of industry. All the data that is produced is stored automatically and can be accessed via the client or the visualizers. If a research project is scheduled by the researcher, he will be given controllability of the heat pump because that's what he wants. Meaning he can now decide, or his algorithm decides when the heat pump should be switched on, by what percentage, and so forth. So the local controller is oversteered. Only a small security layer is still enabled such that the infrastructure cannot be harmed by a researcher accidentally. And this is the same process also for the other interfaces. Typically, experiments are 1 day, 1 week, 1 month, whatever is necessary for the research question at hand or the development question at hand. As we already have heard by Gianfranco Giudati, by one of the previous launch talks on the Remap platform, Remap accesses real hardware, and Remap accesses real hardware at EMPA via this Energy Hub interface. Also in Suite Decarb.ch and Suite Pathfinder, we will use the Ehub, and I'm happy also to announce that now in the living and working suites that will start soon, Energy Hub will also be represented. More specifically, in Pathfinder, we use the setup to have a source of reliable data, and where we can implement case studies for future modeling or having flexibility aware models and case studies showcasing the different uses of flexibility. A component itself is not flexible. A battery is not flexible. How a battery is used can imply flexibility, and how a battery is used in a systemic perspective can leverage flexibility. And for that, we need setups where we can actually implement and test real life how these technologies can be used and can be used differently, deviating from their intended use to provide services to others, i.e. provide flexibility. This is mostly associated to work package 2 and 3 and involves partners at ETH and not just Energy Hub as a local setup, but also the infrastructures at EPFL, as we have heard last time by Mario Pallone, and PSI, which the following launch talk will be about. Ideally, we'll see if in work package 5 in the PND project, the Energy Hub setup can be a sandbox to test the developments before we go to a real district and herd stuff there, that we can sanity check the developments in Ehub first. Limitations is one specific setup which is intended to be used. So no simulation environment. The idea is to go to the system. We have specific energy profiles. So from the people who live there, they behave in a certain way, and this results in energy demand. We can ask people to behave a bit differently, of course, but I mean, this is how it is. In real life, you will see a very specific energy demand. We have no aggregation effects with the 15 people that use or live in Nest, for example. And we cannot control all parameters, again, as it is a more real setup where people live and work. But for that, again, we have a nice link to the Remap simulation environment where we can use their developments to alleviate our limitations a bit. So this is quite a nice collaboration. Okay, last slide. Typical users. We have, of course, the usual suspects when it comes to research institutes or the areas of different research institutes, which is energy management, data science, control. But then also companies who provide technologies, IoT sensors, for example, or services with the collected data that want to know, does their newly developed service actually work in a prototype implementation at Ehub, at Nest, at Move, which is not always research, but mostly development questions, for which the demonstrators are also intended for. When it comes to research, only doing research for research stake is okay, but typically we also have partners in the research projects involved. These are building energy management companies, DSO, so distribution system operators when it comes to electric energy, or energy providers, electric, thermal, or gas. To have a nice loop back to the beginning of the lunch talk, we also see digital ecosystems players as one of our rising partners or category of partners. So people or companies who are not native to energy, buildings, or mobility, but rather to the benchmark sectors, who see quite a value with their already developed tools to already have an impact on energy systems, which have a different kind of aspect to how to deal with data collection, data security, privacy, because these are already established topics there, where with smart meter data, for example, people in the energy sector are more unfamiliar with, or there's still a learning curve to go through. So it's also quite interesting to work with digital ecosystem players when it comes to the energy transition. A more graphic view of the partners that we have been working with and are still working with, you see here, and useful links for your reference if you're interested in more material. Thank you very much for your attention. I hope I was able to bring our setup a bit closer to you and what we do within Suite Pathfinder. Thank you very much.